Okay, welcome back. So if you're watching this, then that means you've completed the activity using the little cardboard spectroscopes we made. Hopefully you were able to identify some sources of light that had different character. And you can see that there are sort of two patterns that you see in the emission of light by natural objects. One thing you see is that things that are fundamentally sort of hot emit broad, continuous spectra of light. The other kind of emission that you see, particularly from things like compact fluorescent bulbs, is light that's broken up into many discrete colors. Now, this can be still something that appears white because of the way that human vision works. So you can, if you have a red light, a green light, and a blue light, you can combine them in a way that tricks your eyes into thinking it's a white light. Um, but there's a big difference. You have these discrete sources that emit light at particular wavelengths, and there are other sources that emit very broad continuous spectra. So normally if we were available, able to meet on campus, we would have you look at discharge lamps showing very particular elements, where even with these little cardboard spectrographs, you can see that there are different patterns of light for different kinds of elements. So neon has this characteristic red-orange color for a discharge, and that has lots and lots of sharp lines in the red and yellow region of the spectrum, whereas something like helium or mercury has a much more distributed, much more widely distributed, widely spaced lines of fewer colors. You can also do this with much better equipment than our little cardboard spectroscopes, and what you find is these patterns of spectral lines for every element in the periodic table has very specific wavelengths of light at which it will absorb or emit radiation. Now, this is an observation that's made in the early 1800s. By the middle of the century, it's absolutely established that every chemical element known has its own unique pattern of these spectral lines. People are using this to identify elements and even to discover new elements. By around 1870 or so, people are announcing the discovery of new elements based on heating up a sample of something and seeing a color of light come out that doesn't match the light emitted by any known substance. The one thing that people don't know about this is why this happens. This is a very mysterious pattern. It's not clear why light should be emitted in these discrete spectral lines if you take a sample of a particular element and excite it in a way that makes it emit light. The key to cracking this ends up being the simplest of the chemical elements, which is hydrogen. And this is started by a school teacher named Johann Balmer, who started looking at the few lines in hydrogen that are visible. There's only 4 or 5 that you can easily see. He looked at these few lines and found that they fit a very particular pattern. And he found a mathematical formula that matched that pattern. And then it turns out you can generalize that to include other regions of the spectrum. If you look at lines that appear in the ultraviolet, you can identify a particular pattern that is the same as the pattern Balmer found for the visible lines. If you look in the infrared, there's another one. This is later generalized by the Swedish physicist Johannes Rydberg into sort of the formula that's our usual modern representation of this. And the pattern that he found is 1 over the wavelength looks like some constant times 2 integers uniquely identify every line in the spectrum of hydrogen, right? And you have 1 over 1 integer squared, 1 over another integer squared. This is a very simple pattern and suggests that there ought to be some sort of simple underlying model. Of course, that's the same thing we said about the blackbody radiation and the photoelectric effect, and those turned out to be completely not simple. And the same thing happens here. People noticed this pattern that was noticed by Balmer and Rydberg, but nobody is able to explain what's going on. So what's going on? Well, we know that light has to be emitted by atoms, and we know that atoms contain electrons. This is known by the 1890s. So people are trying to casting around, trying to figure out what is going on. And the way that you get light waves emitted by a an atom containing electrons is just to shake those electrons back and forth, right? If you shake the electrons up and down, that produces an electric field that's going up and down in different directions. And if the electron shakes at a particular frequency, it produces a wave at a particular frequency. This is the thing that Hertz did, essentially, just on a big scale, making electrons move in big loops back and forth at a particular frequency. This is what we do to generate radio waves all the time in radios, or the antenna of your smartphone. We make electrons move back and forth, and that produces a wave at the frequency that they're moving back and forth. So if we want to get light out of atoms, well, we know that atoms contain electrons. We just need those electrons to move at particular frequencies. We also know that atoms are electrically neutral, right? So that the negatively charged electrons must be counteracted by some sort of positive charge. And so the model in around 1900 is, well, there's sort of this gelatinous blob of positive charge, and it has electrons studded in it. In the memorable phrase that somebody used is that they're like raisins in a plum pudding. You have these little electrons in there, and something's holding those electrons in place inside this positive blob, and that gives them some characteristic frequency at which they oscillate back and forth, and that accounts for these spectral lines. This is, to put it mildly, not a satisfying model, and it gets a whole lot worse in 1909. What happens in 1909? Well, what happens in 1909 is one of the greatest undergraduate research projects in the history of science. A guy named Ernest Marsden showed up at the University of Manchester in 1908, 1909 to work in the lab of Ernest Rutherford. And Rutherford, because Marsden was an undergraduate, delegated him to somebody else, to the German physicist Hans Geiger, who was working with Rutherford. And Geiger was doing experiments where they took alpha particle radiation from a radioactive source, and they were sending the alpha particles at a thin foil of gold. They were doing this because they hoped to learn something about the structure of the gold foil by the alpha particles coming in and sort of being bent as they pass through the gold foil by their interactions with the positively charged blobs that constitute the gold atoms. These, alpha particles should be bent by a few degrees from a straight ahead path as they pass through the foil, and how much they bend and how many get bent tells you something about how the atoms are put together. Marsden was put on this project, and to give him something to do, they asked him to do sort of a sanity check experiment. They asked him to look on the back side of the gold foil, the same side of the foil where the alpha particle source was, and see if there were any alpha particles coming straight back. Right now, obviously, there shouldn't be any alpha particles coming straight back. That's not what they were looking for, but they wanted to know, is there any stray radiation coming around that's going to be throwing off our results? So Marsden was put on this project, supervised by Geiger. And what happened is, it turns out that there are lots of alpha particles backscattered. In fact, there are alpha particles coming almost straight back at the source in very large numbers. This is a really surprising result. This is not supposed to happen. Marsden and Geiger's boss, Ernest Rutherford, described it later as quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Right? That's how shocking this is. Okay, why is it shocking? It's shocking because Rutherford knew that the only way to throw a projectile at an object and have it come backwards after the collision is for it to hit something that's much, much more massive than the projectile that you're sending in. So these alpha particles that they're sending in must be hitting something very small and solid that has most of the mass of the atom in it. This is incredibly surprising because this is not the picture that people had of atoms. Instead, the picture you have to have is the cartoon that we have now of an atom like a little solar system with a positively charged nucleus at the center that contains nearly all of the mass and electrons sort of around the outside. Right. The gelatinous blob atom that people had in mind before this simply would not be able to deflect the alpha particles to send any of them straight back at the source. So Rutherford came up with this new model of the atom with a positive nucleus at the center and the electrons orbiting around the outside. This makes a very satisfying sort of cartoon picture, right? You can think of the atom like a little solar system. This is a cartoon version of an atom that we have now. And we know now that this is the way things work. You have a positive nucleus that has 99.9% of the mass of the atom in it. That nucleus is about 10 to the minus 15 meters across. That's a 1/4 of a meter across. And the electrons orbit outside the nucleus, and the orbits of the electrons are about 100,000 times bigger around than the size of the nucleus. So the nucleus has been described memorably as an object like a fly in a cathedral, right? It's a tiny little object in a vast space inside those electron orbits. This is a nice picture in a lot of ways. It explains the Marsden and Geiger results. It has one tiny little problem, which is it cannot possibly work in classical physics. Why is that? Well, we already said the reason. How do you make radiation with electrons? You make radiation by making electrons move back and forth. Well, an electron that's going around in a circle, right, orbiting the nucleus, that electron ought to be spitting out radiation. It ought to be spitting out an enormous burst of X-rays, right? But that radiation is going to carry away some energy, which means that the electron should be losing energy, and the electron's orbit should decay. It should just spiral in and crash into the nucleus and stop being something like an atom, right? Rutherford's atom is a nice cartoon picture. It's a complete disaster from the standpoint of classical physics. So how do we fix this? Well, we've sort of seen the outlines of a solution before, which is to make just a radical assertion about the nature of matter being different than everybody thought it was. And this comes from the Danish theoretical physicist Niels Bohr, who was working with Rutherford. And Bohr introduced in 1913 the first quantum model of an atom. And what he said is essentially that, atoms are manifestly a thing that exists. They don't just spew out X-rays and decay into the nucleus, but we know that the nucleus has to be there. We know that the atom has to be much bigger. So we're just going to change the rules. And he said there are certain special orbits inside an atom in which an electron simply does not emit any radiation. Okay, just by fiat assert that. And he said that the absorption and emission occurs only when an electron moves between two of these orbits. So you move from a small radius orbit to a larger radius orbit. When that happens, then you emit some light. When you emit the light, the frequency of the light that gets emitted depends on the difference between the energy of the orbit you started in and the orbit that you ended in. And the rule for determining how the frequency depends on the energy difference is just the rule that Planck and Einstein introduced for the photon, right? The energy is Planck's constant times the frequency of the light. And then you need a way to pick out which of these orbits are special, right? Which are the ones for which the electron doesn't emit any radiation. And the rule that Bohr introduced for the special orbits is that they have a property called angular momentum, that is an integer multiple of Planck's constant divided by 2 pi. Okay. So this is, again, going back to something very much like the ideas that Planck and Einstein had when they were making their quantum theories about light, right? It's an integer multiple of something that has to do with Planck's constant. Right. Bohr put this out just saying, let's just assert that there are certain special orbits, they have these properties, and let's see what happens. Right. If you then work through the consequences of this model, you find some very nice things. You find that you get atoms that are stable with well-defined orbits. You can, putting these parameters in gives you orbits that have a definite radius. If you calculate what is the size of those orbits, you get that the atoms are about 1/10 of a nanometer across, which is about the right size. We know from other experiments that this is the size that atoms are. You can predict how much energy is required to entirely remove the electron from a hydrogen atom, and you get a value that is just about right. So this Bohr model of hydrogen works really well at matching parameters that we'd previously seen. It also works very well for explaining some features of X-ray emission spectra, which was another thing that was being studied in Rutherford's lab. It is another of the things that really got Bohr onto this problem. The most important thing, though, is it explains the Rydberg formula. Because when you calculate what are the energies of these energy states that are special, these special orbits where the electrons don't emit, what you find is that they have energies that look like some characteristic energy for the atom as a whole divided by an integer squared. So you can number these orbits with an integer, right? Each orbit has an energy that is the ground state energy divided by that integer squared, and everything works great. The difference in energy between two states is going to look like some numbers times 1 over an integer squared minus 1 over another integer squared. That's exactly what the Rydberg formula is. So all of this works great. The Bohr model is fantastic for explaining hydrogen. This has one tiny little problem, which is, why are these states special? What is it about states with integer angular momentum that makes them special, that sets them apart from all the other orbits, that would give you some justification for these being states that don't emit any radiation? That's a very important question, and answering that question takes us to some very weird places. But this lecture has gone on for a little while now, so I'll cut it off here and make another video, and you can look at that one for the answer. So we'll see you then.